We are in the final lesson of inverses for Unit 3, our inverses and polynomial functions. Today, in this lesson, we are going to verify functions to be inverses of one another. So there's a couple of steps that we take, and either they are or they are not inverses. So follow along and pause and repeat as needed. All right, to verify that we have inverses, we need to prove the functions are inverses by using their compositions. And that means that we are going to show that f of g of x equals x and show that g of f of x equals x. So what we're going to do is we're going to complete both compositions, and they both have to equal x. If they do not, then the functions are not inverses. Okay, and that composition means you're going to, instead of substituting a number for x to get a y value, we're going to take a function and put it inside of the other function. It sounds a little weird, just stick with me, we'll get through it. Okay, so that composition f of g of x has to equal x, and g of f of x has to equal x. If both of them don't equal x, those compositions, then the functions are not inverses. We'll have some that are and some that are not. Not everything has to be an inverse. Okay, so these examples are all going to say verify the functions are inverses. It doesn't mean that they are. We're going to prove it by doing the composition. So we're going to start with f of g. So anywhere I see an x in the original f of x function, I'm going to substitute it with the g of x function. So f of g of x is 1/2 multiplied by g of x plus 3. Okay, our original f of x is 1/2 x plus 3. Our original g of x is 2x minus 6. So our next step in the composition f of g, this is going to be f of g equals 1/2 multiplied by that quantity, the g of x function, of 2x minus 6, and then plus 3. Now we're just going to clean up the mess. You did the hard part. Now you got regular algebra stuff we're going to take care of. Multiply by 1/2 to each of the terms inside. 1/2 multiplied by the 2x is going to give me x, and 1/2 multiplied by the -6 will give me a -3. So that will simplify to give us x minus 3 plus 3. And when we completely simplify that statement, we get f of g of x to equal x. That's exactly what we want. So checkmate. So far, so good. Okay. I should just say check, not checkmate. All right, our next example. G of x is 2x minus 6. So now we want to evaluate and do the composition g of f of x. So that's going to be 2 multiplied by f of x minus 6. That will give us 2 multiplied by the quantity of 1/2 x plus 3, that's the other function, minus 6. And then we're going to distribute 2 multiplied by 1/2 x. 2 multiplied by 1/2 is 1. 1 times x is x. 2 multiplied by a positive 3 is a positive 6. So that gives me an x plus 6 and then minus the 6. And when we combine like terms, we get g of f of x to also equal x. That's exactly what we wanted. Since both compositions equaled x, that means that the functions are inverses. That means they reflect over the line y equals x that we did in the very first lesson of inverses. We looked to see the graphs. Do they reflect each other? Perfect. All right, we have a few more. Let's skedaddle through them. Here we go. Example 2, we have f of x to equal the square root of x minus 2 plus 5, and g of x to equal the quantity x minus 5 squared plus 2. So our first function is a square root function. G of x is a quadratic or a parabola because it's raised to the second power. So we need to do f of g of x. So that will be the square root of g of x minus 2 plus 5, which will give us the square root of the quantity of x minus 5 squared plus 2 minus the 2 that's already under the radical, and then plus 5. All right, we're going to clean up the stuff inside the radical. Plus 2 minus 2 undoes itself. So now we have the square root of the quantity of x minus 5 squared, and then plus 5. Hey, we've seen this a couple times already. The square root and the second power undo each other, leaving us with x minus 5 plus the other 5. Therefore, f of g of x does simplify just to give us x, because the positive 5 and the negative 5 undo each other as well. All right, we've got to check the next composition, make sure it works over here as well. G of f of x will become the quantity of f of x minus 5 squared plus 2. Okay, so wherever I see that f of x, I got to substitute that function in. So it's the quantity of, here's a whole lot of stuff, the square root of x minus 2 plus 5, all of that is just f of x, minus the 5, quantity squared, and then plus 2. Okay, like we did in the last one, clean up the stuff that we can. So plus 5 minus 5, these little guys right here, those undo each other, leaving us with the quantity squared of the square root of x minus 2 plus 2. Again, we saw that the square root and the second power undo each other. So g of f of x is now x minus 2 plus 2, simplifies to give us x. Perfect. So that proves that since the compositions f of g and g of f both equal x, they reflect that line y equals x, and these two functions again are inverses. Okay, there's got to be some that aren't. Let's see if we can come across one. All right, example 3. F of x is 3x to the 5th power. G of x is the 5th root of x divided by 3. All right, let's check this one. It looks really yucky, but let's substitute in and see what happens. Let's evaluate. What is f of g of x? That would be 3 multiplied by g of x to the 5th power, which would be 3 multiplied by the 5th root of x over 3 raised to the 5th power. Okay, so a 5th root and a 5th power. Those undo each other. That leaves me with 3 multiplied by x divided by 3. Okay, cool. If I multiply by 3 and divide by 3, that's awesome. You can write 3x over 3, or you can just simplify the 3's. So that first composition, f of g of x, does equal x. Good. That's exactly what we want. I think we might get another inverse, guys. Let's check it. Keep working it through. G of f of x will be the 5th root of f of x divided by 3. Okay? That'll be the 5th root of 3x to the 5th divided by 3. As always, clean up, simplify. Multiplying by 3 and dividing by 3 are inverse operations. They undo one another. So this composition now simplifies to give us the 5th root of x to the 5th. We already saw that simplify in the other part. The 5th root of x to the 5th simplifies. So g of f of x is also equal to x. All right, we got our third one in a row. These two functions are inverses. All right, keep. Okay, j of x is negative 3x over 2 plus 7 over 2, and k of x is 3x minus 7. All right, so let's do j of k of x. So that would be negative 3 multiplied by k of x divided by 2 plus 7 over 2. Okay, substitute in. It looks kind of yuck. Now remember, you guys, you don't have to write this step right here. You don't have to show that. I do it so that we can really see truly what we're doing. You can jump to the next part that we show. So j of k of x equals negative 3 multiplied by the quantity of 3x minus 7, all divided by 2. Okay, let's simplify, see what we get. Multiply 3 to both of the terms inside. So 3 multiplied by 3x is a 9x. 3 multiplied by -7 is a -21. And I'm just keeping that negative on the outside of the fraction. So that gives me a negative 9x minus 21 all over 2 plus 7 over 2. Okay, if we were to simplify this stuff out a little bit farther, we really wouldn't get very far with it. I'd get a negative 9x over 2 and then plus a 21 over 2 plus a 7 over 2. That is not going to simplify. So in this one, j of x and k of x are not inverses because there's no way to make j of k of x equal to x. Like, we can't simplify it down any farther. There we go. We got one that didn't work. See, I told you not everything has to work. All right, let's try a few more, see how we keep going with this process. You could also have checked k of j of x and worked the problem the other way. You still would have ended up with a very similar equation. However, it would not simplify to give you an x. Okay, so you can go either way with these. Check whichever composition you like to do first. Okay, example 5. This is our last one for verifying that functions are inverses. We're given m of x equals the quantity x minus 2 cubed minus 4, and n of x equals the cubed root of x plus 4 plus 2. We'll first check m of n of x. That would be that n of x minus 2, the quantity cubed minus 4. That, don't forget that first part. You don't have to write this step. I just do it to kind of help us out, showing that the x is being replaced with the other function. You can jump to what we're going to do next. M of n of x equals the cubed root of x plus 4 plus 2. All of that part I just read is n of x. Minus 2 all raised to the third power, and then minus 4. Whatever's in parentheses that you can combine to eliminate like terms, positive 2 and negative 2, simplify as best you can. So our composition is now the cubed root of x plus 4 all raised to the third power, or all cubed. The cube root and the third power undo each other, leaving us with x plus 4 minus 4. So m of n of x equals x. That's exactly what we want. Yay. That means we have to check the second. We got to do n of m. We got to check this composition. So n of m of x will equal the cubed root of m of x plus 4 and then plus 2. Remember, we're replacing this m of x function with that next step. The cubed root of the quantity of x minus 2 cubed minus 4, that's m of x, plus the 4 that was already under the radical, and then plus 2 outside the radical. As always, clean up any terms that you can combine. A negative 4 and a positive 4 undo each other, leaving us with the cubed root of the quantity of x minus 2 cubed plus 2. Cube root and the third power, or cubing something we just saw, undoes itself. That will leave us with n of m of x, that composition equaling x minus 2 plus 2, which is just x. This is perfect. We have proven, again, these two functions reflect the line y equals x because their compositions are x. And that means that the functions are inverses. Great job with this lesson. Super proud of you guys. Let us know if we can help you out with anything. Have a great day.